regard to also this one's called Crocs or what? In the second I had the tire shoes, and after passing and campus, some guy also started putting them on. But it seems there's a secret in the tire shoes. So these are just Crocs. They are not tire shoes. You put on once and for all, remember, you don't have to replace. And you don't care whether in the mud or in the dust or whatever, you just do like this in the water, it is green again. After teaching you this is the third time, isn't it? I have nothing to care about you anymore. That's why I don't care. I think that's why teachers are always taken like as if they are poor. Because you are with the same students every day. Why look nice? Just go and spit fire. I mean, they matter. Give them matter and that's it. You are with the kids in the morning, in the evening, and then you still have to iron the shirt for what? Washing you do because it is hygienic. But ironing for what? Okay, so we had started on the uniqueness theorem. And on the uniqueness theorem, we had said that if we have two values or two solutions, V1 and V2, and both of these satisfy Laplace's equation, then of course the Laplacian of either of them will be equal. So the Laplacian equation will be satisfied for this solution and also for this other solution. And so would be there difference. So we have squared V2 minus V1 is also equal to. That's where we had scribbled and read. So we start from there and now move on to each solution must also satisfy each solution must also satisfy beyond the Laplacian equation, must also satisfy the boundary conditions. The boundary conditions. And if we represent the given potential, the V, we present the given potential values on the boundaries by VB, on the boundaries by VB. This is potential at the interface, boundary from medium 1 to medium 2. Then the value of V1 on the boundary, the value of V1 on the boundary. We this is V1B at the boundary, and the value of V2 and the value of V2 at the boundary or on the boundary is V2B must be identical to VB, must be similar, identical to VB. What I'm saying is that if you got a boundary of, let's say you're looking for a potential, I have suffered with flu since weekend. I don't know what happened. And then I left the germs in the office. I had improved when I reached the office. I again picked them up. What speed of our flu? That's 5 mg. Then you say, Kasha, you say what?
You can go to the university.
You and who? You and who now? Because are you also having flu?
Yes.
Have you been there? I think there's a problem because many people are sneezing around. I mean,
Please for the week.
hey, my friend, speak slowly. I think I've never seen you with the flu. So if this is our boundary, okay, and this is our medium 1, this is medium 2, and we were saying that there is potential V2 in this boundary, I mean in this other medium, and V1 in this medium. Just at the interface, we are saying that the V2B and V1B are identical to the one at the exact at the boundary, the VB, because of if you are too close to the boundary to make sure that the two can be. So we are trying to make sure that we, just like the way they say that, tell me the people you walk around with, then I tell you who you are. In Uganda, how do they say it? Kauma. Ujja kuwoyita naye kuwulire kikyoli. I'm looking for the one whom I can use as an example. I'm not seeing the one I wanted to use as an example. If I saw this one, then I would know. I think it is true. Those old people were really smart. They were making those sayings out of experience. So then, eventually, these two for V1B and the value V2B must be identical to VB at the end of the day. So that means that V1B is equal to the V, since they are identical to each other and identical to VB, equal to V2B, and all of them are identical with VB. And this implies that V1B, or you can, if you want, you can use V2B, V1B minus V2B equals to 0. If they are identical, when you subtract them, you get to 0. Now consider, I hope have you tried to check out the identities to know when I'm using identities where I'm coming from? Samantha? covered enough for you to suffer in a test? Hey, if I don't use that word, you don't find it serious. Okay, to enjoy the test, if that is, haven't we covered enough for you to enjoy a test? Mahad, you have. Okay. Maybe that way you start now knowing where we are. So consider the vector identity. Consider the vector identity, which says that the divergence of, remember, the divergence of VB being the same as, we said we get the scalar divergence of the vector, then add of the vector dotted with the scalar with the, the gradient operator, applied with the scalar, which of course will make it the vector. So this is the D dot grad V. So when we use this one, then we can write our expression in a way that this difference in potential in the way of the vector by multiplying by the gradient operator, and then the scalar, the difference. So which holds for any, this identity holds for any scalar V and any vector D. And any vector D. So put or let V1 minus V2 be the scalar, and then grad V1 minus V2 as the vector. And then the rest is as you like. A nice chalk is getting finished. The new chalk was really fake. Don't worry, I'll make it. So I now substitute in this expression, I substitute for the vector D, it is grad V1 minus V2. Then for the scalar V, it is V1 minus V2 alone. Do you do math or you just go there to get marks? You go chop and forget. The D in this expression here, we are having it as grad V1 minus, and then the V in this vector, we are having it as V1 minus, and then I substitute, the expression for this vector. So this would imply that then the divergence of VD, which is V1, so this is the divergence of V1 minus V2, that is our scalar, into our vector, which is gradient, gradient operator into the V1 minus V2, and this is this part here, and then it will equal the right hand side, part. So then we say that this would imply that the divergence of V1 minus V2 in times the vector which is grad V1 minus V2 would be equal to the scalar which is V1 minus V2 and then inu, the divergence of the vector which is divergence of the grad V1 minus V2, and then I add on the vector which is grad V1 minus V2, and then dotted with the grad V, which is the same as grad V1 minus V2. And I don't need to do anything other than having this together for avoiding confusion. Is that okay? Yes. Okay, so integrating the expression throughout, if we did integrate on the left and the right, integrating the expression throughout, the volume, throughout the volume, enclosed by the boundary surface, enclosed by the boundary surface, enclosed by the boundary surface. Then we will have the integral of the left-hand side, which is the integral divergence of V1 minus V2 in grad V1 minus V2 equals to, so we are doing this over the volume of the volume bounded by or enclosed by the boundary surface, and this would be the tau, would be the same as integral over the volume tau V1 minus V2. This is the scalar V in the divergence of the vector, which vector is defined by the gradient over here times the V1 minus V2, and then we integrating over the volume with respect to the volume tau, and finally we add on the integral over the volume tau, this is the vector which is V1 minus V2, grad V1 minus V2, then dotted with the grad V, which is grad V1 minus V2, and we are doing this integral over the volume tau enclosed by the boundary surface. And if you do the using TWINAMASIKO Benon theorem, and then we can find that the left-hand side, which is the divergence of the vector, the tau, can be changed into the surface, back into the surface integral. Using TWINAMASIKO Benon theorem. How many of you write your names if you are not writing on the examination paper? Benon theorem. we have the left-hand side gives, the left-hand side yields, it becomes a surface, we can integrate over the boundary surface S, and then we change the vector, this whole thing which we are dotting this whole thing, the tau, that is, we are taking the divergence of this whole thing, we are dotting the gradient operator and this whole thing, so that means we get this whole thing which we were diverging, dotted with ds, and then we would have now changed it back to the surface. So that whole thing is V1 minus V2, then grad V1 minus V2, and this we dot it with ds or MDS. So to just have the uniformity with the knots, we dot it with a unit direction vector normal to the boundary surface, then this, and this should be equal to, when you integrate along the surface and you go all the way to the enclosure, what do you get? Huh? If you integrate over the surface, what do you get? This is V. This is so this is the S, the V. No, before I even do that, if you are integrating over the boundary surface and you are going across and close the crease closed integral, closed group integral across the whole boundary surface, what do you get? Guys, you need to wake up and make your life easy. This is equal to 0. And since V1, since V1B equals to V2B. The integrand is the one which can only make this 0, because we have our integrand, part of this integrand here, whether you are taking the gradient of this, but this one mainly, since these are identical, and we had said that at the boundary we have V1B equal to V2B, then this makes this integral to be 0. Hence, this was the left-hand side, so the right-hand side, this bed here, which is the integral over the volume tau, V1 minus V2 in the divergence of the grad V1 minus V2, then the tau, plus integral over the volume tau, grad V1 minus V2, and that. So maybe I should put this one in these brackets, and then that with the grad V1 minus V2. Do I do this also? The dA is equal to the left-hand side, which we were established is equal to this is the same as here. This is the same as grad squared V1 minus V2. So, but what would it be when you take grad squared V1 minus V2? What do you get? when V1 is almost identical, I mean is identical to V2 at the boundary. So we have but grad squared V1 minus V2 equals to 0. Then not somewhere if I miss a V or a 1, please cross check. But like I said, it is algebraic gymnastics. Once you know what you are doing, it should flow. And the more you practice, the more it flows. You can't go in this course and then you are cramming, just reading like a newspaper. You will get nothing. Just look at the expression, you get a piece of paper, try to go through. Otherwise, these people will say, this one I've seen. when you close the book, you say, but what did I see? There are a bunch of V1 minus V2, V1 minus 2. How do you get this one in the head? So just now know you are coming from here, then when you reach here, you just do it in your, you start doing it. Then where you mess up, you go cross check. That is the principle of I see, forget, here, forget, do, remember. So this has gone to 0, and if this goes to 0, it kills off. And then the only surviving thing is this one here. And when you look at them, they look like they are the same. And then that means this will end up having grad V1 minus V2 squared. So this would imply that integral over the volume term, grad V1 minus V2 squared over the volume term equals to 0. So we are closing in on getting something fairly next to what we want to get. In this case here, the integrand what you are integrating is called an integrand, should be 0. Should be 0 because grad V1 minus V2 squared cannot be negative. Cannot be negative for any other reason. If there is no other reason for this integral to be 0 other than the integral being equal to 0. And that means that because the other ones are just an integral instruction, this integral with the tau for respect, with respect what you are integrating with respect to. So for this whole integral to be equal to 0, it must be emanating from this place. And we can't have negative values. Everything that happens here, even if it becomes negative, this square ends up in making it positive. Hence, the integrand is equal to, is the one which is equal to 0. Grad V1 minus V2 squared equals 0. And we take square root both sides. What is the square root of 0? When you have nothing, it's like you have no worries. You have nothing. You have no chicken, you have no cow, you have no wife, you have no friend, you have no problems. You are 0. You are 0. You don't care. You can't. You would have any problems. You had nothing. It's like what? There are people who just walk around and find you with family they eat. They don't mind. If they don't have it, they just starve. They are not better. So, of course, when you, this is a differentiation, if you are, this is inside this one, there is a differentiation. The I kali by kali x j plus j kali by kali y plus k kali by kali z. So that means that if this is differentiation and this is what you are differentiating is giving you 0, then what is the characteristic of this something you are differentiating? It's a constant. So V1 minus V2 equals some constant. So now that we have reached this part of reaching the difference V1 minus V2 becoming equaling to a constant, you tickle that thing to come out. The teeth. Do you have a door at home? You close the door. I have heard this man ignite me forever. I will make you tough. You know, there are these guys who come and they want to act tough, so you also tighten them. Make sure that they realize that they need to be tough. Like Fred now is a good boy. Yeah. So considering the boundary point, is it boundary point or points? So V1 minus V2 can be related in terms of the boundary, the boundary points, which is the V1 here, the V1B and V2B. So this is equal to V1B minus V2, and we have already said that this is equal to a constant. And if we consider this boundary, previously we had said this one is the identical. So if they are identical, then it gives their difference gives you 0. So if the difference between these, we had said because of this differentiation is a constant, and the difference is giving us 0. So what is this damn constant? 0. So yes. So the constant equals to, I had the next use, yes?
At the point where we use the divergence theorem, did we
The TWINAMASIKO theorem, for your correction.
we were considering the boundary because we later concluded that it's equal to 0 because V1B is equal to V2. So we considering that the boundary is so where we say the left hand side was equal to 0.
I'm just trying to understand the concept. I know when we took the integral over the surface S and we had the divergence of the vector, this was no, this one. Remind me, I don't remember this. So grad V1 minus V2,
Yes.
V1 minus V2, then grad or the dot, because it can't be a dot,
Then V1 minus V2.
grad.
V1 minus V2.
Then we now dotted it with n
Yes, and
equaling to 0.
yes.
Your concern is?
So at that point, we say that that part is equal to 0 because V1B is equal to V2B. So we are considering the boundaries. V1 minus V2 and then I'm saying it is
Yeah, and that's why I'm looking for the best explanation of this. Of course, we have a bunch of V1s minus V2, so if we say V1 is equal to V2 and then we are saying that's what is causing 0, then we would have who is good at math? Kasada. Will you help me? The what? You are a physics major. Do we have a math major? Yes. Who? Najuma. Help us. I am trying to look for the, since she's now not disagreeing, but saying that we changed the. So I think now you are right, and the problem you don't want to hit the nail at the top. Samantha, you don't want to tell me that in the notes it is at the boundary. No, in the notes it is the 1B, 2B in the expression, which I didn't write. And that's why it was becoming 0. You wrote it?
yes.
The B's, the 1B, the 2B's.
Yes.
Is that how I wrote it?
Since. After stating that, you say since V1B.
Yeah, but the B's are everywhere here.
Oh.
So that's why I'm saying that I wish you had checked on the notes. And I didn't write that, but on the reason everything is becoming 0 is that we consider that the boundary at the surface, we change it to the surface and the boundary to make sure that we use the boundary values. And that's why it became 0. So, and then I said since the notes are elaborative. You people want me to be so keen on the notes, and sometimes I'm lousy and assume that since you are all accessible, whether you will be able to check it out. So now I think we are good. So now that we have the constant being equal to 0, I mean the V1, V2 minus V2 being a constant, and then we consider the boundary and this difference is 0, and the constant was equal to V1 minus V2, which is identical to V1B minus V2B. So our constant is 0. Hence, after all this nonsense, okay, after going all around looking at the uniqueness of V1 and V2, we can now proudly say that V1 is equal to V2. And this is giving two identical solutions. We have just begun. This is just a jaribu. So the algebraic gymnastics. Yes. Of what? Of is when you go to a market and you look at the nuts and they are looking yummy. You know what yummy means? They are looking good. So you see, can you give me like 2 or 3 and I test?
Sample.
And then you sample them. That's that is Jaribu. You had ever had somewhere, so I had it somewhere and you were confused. You know, a student came here and reached Mulango, and then the guy, oh no, we were in, actually this is the true story, we were in our hall of residence. In the first year we were 10 guys. Our annex was separated, so I think we were two, so we were 6 here, 4 inside, 2 decades there, 3 decades here. So one time these guys who had gone to Mulago were conversing, saying, today they brought a cadaver, I think it had gotten an accident or something like that. But some of them were looking so good, so he said, can you get me one? He didn't know what a cadaver was. Does anyone of you know, is anyone of you not knowing what a cadaver is? Still, Kadu doesn't know. A cadaver is a dead body, but that's the language of the medical school. So this fellow who was doing civil engineering thought maybe a cadaver is some cute lady. Like some cute lady in Mulago. So he said, so can I get one cadaver also? And, so that's why I'm trying to explain to Kadu. He could have been offered Janibu. And then he didn't really find out, I mean, get the idea of what they were offering. So now he knows. So this is uniqueness theorem. This is uniqueness theorem. Okay. This uniqueness, you should not make me overtalk. This uniqueness theorem also applies to we have been able to apply it to Laplace's equation. We can also apply it to Poisson's equation. And if we apply it to Poisson's equation for if the grad squared V is equal to minus rho of epsilon, then, for if grad squared V1 equals to rho of epsilon and grad squared V2 equals to minus rho of epsilon, then we can have the grad squared V1 minus V2 being the difference on the right hand side, and that would be equal to 0. So we got the then grad squared V1 minus V2. Now that's why you normally see me always copying from the note, because a simple mishap on the not including the 1B, 2B now was causing us problems. And then this is equal to 0 as before. So boundary conditions still require that. At the boundary, we need to know boundary conditions still require that. Still require that. At the boundary, V1B minus V2B equals to 0. That's it. That's all about the uniqueness theorem and the boundary conditions. Now we can comfortably know that as long as we are on the boundary, then the potential across the boundary is almost there. the same. That helps us to make sure that we work out a couple of settings of charge distributions. And so we start from, now that we have an idea, we start on the examples of how to solve Laplacian equations, and start by using the Nellicon. So is it Nellicon or Backhouse? Start with the backhouse. I used to think it is the back of the house until when I discovered that it was a man. Because they said, today we are in the back, we are going in the backhouse. So I was like, what the hell is backhouse? Just like how we go now. So yesterday, if I may share with you, yesterday 2 kids came here. They told me they are candidates in S4. So I said, what the hell do you want? They were both men. I don't deal with females. If they were female, I would just say, I'm busy. It's my right. I have rights. You can't negate my rights. Okay, that's on the sideline. So these kids come and they have a board, some wooden stuff with some USB, whatever, port, then the legs, and then the motor. So they say, sir, one was having problems in English, very bad grammar. And they are from Colorado High School. I recorded the session so you can hear. I am going to get that time of buffaloes and then yeah, I'm going to do that so that because once we agreed that I take them through let me start from the beginning. So the one comes and says, we have our idea, we innovated how to create energy, and we have a hand-powered generator. So he gets the thing, starts turning with his hands. So they add some leads, they start beeping. Bleeping, 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 the light is coming up. And so I say, okay. So I said, do you know anything about the DC generator and the AC generator? Yeah, we have researched this. Okay. So I went on the board and started chopping, showed them how AC becomes DC, then the DC motor. So I said, are you still innovators? Or you were just demonstrating then I got my coil and made for them some current. So I asked them, are you still innovating, or now you are just demonstrating that you can make some electricity? They said, surely we are now making just a demonstration that we are making some kind of electricity. Now, what surprised me, they said, but you know what? We need to submit this work to you for UNEP, and they need a letter showing that we consulted. A member also saw it. So I'm like, what the hell is this? And you just come, bragging that you innovated. I've already showed you that you're not innovating, and now you didn't consult with me, and they were saying that the deadline is today for submission. So I was like, what is going on? But because I was interested to get information from first hand, so I asked them, how is the new curriculum? The one who was always quiet was like, no, I like this curriculum now. We can argue, we can present our work those days. I said, which days? The one of primary, you wouldn't be allowed to express yourself. You wouldn't explain anything. The teacher will come, give you his stuff, and that's it. So I asked him, whenever you will go home, who will stop you from explaining to your mother or father or brother or anybody? Whenever you were in games or in break, who was preventing you from explaining? Or because for me, the reason you see being able to try to explain stuff is that anything that I would understand, I would try to explain to friends, colleagues, the classmates. Some of them would swell their hearts. Instead of getting what I'm explaining, they are feeling bad. Me, I went on. Now I'm chopping numbers for you. So there is nobody who was stopping you from discussing in the old curriculum. The challenge we had was apparatus, true or false. Now they have to use projects. So physics, chemistry, biology, and mathematics, partly. How do you argue about the points? How do you argue about the experiment, distillation? Do you have any other chance of distillation? Is there any other method than just heating stuff to steam, then cool down the steam and get a distilled liquid? And then all the chaff and the dirt is left down there where you had left. Is there any other chance you can separate salt from mud other than, dissolving in a salt, make a thorough solution, then filter out, then the filtrate you get, you burn it up, heat it up, the water will evaporate as steam and then leave you with the salt and then you can use it. You don't debate about that. Neither can you debate about the Faraday's law. There is no other thing. It's when you have a conductor carrying through the air. So, I said they are just making you arguing robots. You now argue with the empty heads. Then they were looking at me like, because look, the old curriculum will give you a lot of matter which is theoretical. But if you got a chance to go to a place where they have apparatus, every theory will be here. These chaps now, they go with their heads high because they can talk. But this one was having broken grammar. So I agreed and wrote them a letter. And I was categorical in the letter because I told them, this is such to confirm that I have met so and so who were presenting to me an innovation that turned out to be a demonstration. And I wish them good luck. I signed it. But the reason I gave them a letter is to get evidence that I know how shabby this curriculum is. You can't send people's children to go around looking for a member of society to explain the idea, and then that person confirms that it is a good idea. What if they bribe me? They come and his father says, I want my son to pass, I want to send him to London, please let his project, or tell us which project we can do, or formulate, you go to Katwe, make for us a project, coach these kids to be able to explain it, and then they hand it into you know. All in all, we are going to produce argumentative kids with empty heads. Yes, in all the curriculum you will teach from the beginning to the end, the syllabus wouldn't be finished. Now you are having these discussions and presentations, and I hear computer-aided whatever, they are coming and being in groups, and then you expect to finish the syllabus? It was shortened. So when you shorten things, people become more smarter or they become more dense? More dense. And then there were these arguments, including the curriculum advertisement, that they are trying to make it simpler, that there are a lot of terminologies which are hard.
The content is too sharp.
Eureka experiment is because of Eureka. It's a Biansi. The Archimedes principle is because of the Tulituka, somehow. How am I going to simplify Tulituka? We are singing Gauss's law, Gauss's divergence. All this we are singing Gauss. Gauss is a man. How am I going to simplify him? Government failed to buy apparatus. Now said you go and get all the trash you can, pretend that you are learning physics. And then they expect you to compete with children in China, children in the UK, children in the US. With that shabby knowledge you got, people come with cuttings and then they say, we are making a model of a model. They come with the tin foil, the aluminum foil, then they say we are making a solar cooker. examples of solution of Laplace's equation. So we're going to do examples on how we can solve Laplace's equation. And let's start with the direct integration. Direct integration. Remember, Laplace's equation is grad squared v equals to differentiate second differential equals second order differential equals equal to 0, meaning that we can integrate the first time, get a constant, integrate the second time, then look for the bound, the constant of integration, use the boundary conditions, get the equation, or get a integral. So case 1, we start small. We're going to start small. So like they teach you either, I don't know whether it is curriculum or which one they teach you this, chronology. You start from the simplest of the concept as you complicate it slowly. It's called, there's a good terminology. You have a frog in water, and this frog in water, you heat up the water. So the frog feels it is warming up, even it starts like those here. You increase. By the time it is hot, it can't jump out. So that's how the government is cooking us. You know, they made it look like it is normal. Now we are in the temperature is getting higher. We can't jump out. We're just there. Anything disappear, anything doesn't work, we are okay. We are there. And we are heated up. So we start with case 1, just simple direct integration. So we suppose, since we are starting small, we suppose that potential is varying in only one direction. And we are starting with the Cartesian coordinates. So assuming that we have the potential which is varying along the x. So if this was our y, this is our x, and this is our z. Assuming the potential is varying along this place alone. There is nothing, no potential there, no potential there. So we just assume it is along the x. So suppose the electric potential V, is a function of only x. Is a function of only x. In other words, the potential is varying as, so I don't know, I have two ways of writing x. Sometimes I do this, sometimes I do this. So which one looks nice for you? The second one.
The first one.
The second one.
The second one doesn't make sense.
Come on, there are people who write x by doing like this. Then there are those who write like this. So which one is which? The other one is like chi x, but chi has one side curved like this, and then the other one is just straight, but chi is bigger. How do you survive? God's grace. So Laplace's equation reduces to,
I think the second one.
Laplace's equation, we have agreed on the second one.
Yes.
Good. So Laplace's equation reduces to, so now we have grad squared v. So since it is along one, if you have the grad v, I mean gradient operator will be Kali by Kali x, because you are partially differentiating along the x, partially differentiating along the y, and partially differentiating along the. If you don't have y and z, then that means you can take it as a full derivative. So the squared v Vx squared will equal to 0. This is our Laplacian equation if we are only having along the one, along one variable, that is along the x. The rest is, so integrating twice, we obtain, integrating twice, we obtain, we integrate once, it equals to a constant a. We integrate twice, it becomes ax plus b, another constant. So if we do that at a go, we obtain Vx equaling to ax plus, where a and b are constants of integration, where a and b are constants of integration and are determined by, they are constants of integration and are determined by, or are determined only from where? Variable, so only from the boundary conditions. That's why we have the heading boundary conditions and uniqueness theorem. So boundary conditions, not boundaries. So since we are now in boundaries, let Vx1 equal to V1 and Vx2 equal to V2. Then we have two equations. We have Vx1 equaling to ax1 plus b, and Vx2 equaling to ax2 plus b. We want to get the constants. So if we want to get the constants, we can now look for them from these equations 1 and 2. So we got the, this is equation 1, and this is equation 2. Then remember these ones are also equal to, so I shouldn't be having the x's in the brackets, since we have already said that Vx1 equal to V1 and Vx2 equals to V2. So we can have V1 and V2 at this stage. So V1 equals to Ax1 and V2 equals to Ax2 plus V. And from equation 1, we can have subtract the two of the, so equation 1 minus equation 2, equation 1 minus 2 implies that we have V1 minus V2 is equal to A inu x1 minus the B disappears. This would imply that A would be equal to V1 minus V2 over x1 minus x2. That is the A. B, from equation, if we can use equation 1, x1, which is equal to v1 minus v1 minus v2 into x1 over x1 plus, I mean minus x2. So we have v1. So A would be equal to, in summary, thus A would be equal to v1 minus v2 over x1 minus x2, and B would be equal to v1 x1 minus v1 x2 minus v1 x1 plus v2 x1 over x1 minus x2. This is similar to this. Okay? And this would reduce to v2 x1 minus v1 x2 over x1 minus. So B is equal to the whole of that, v2 x1 minus v1 x2 over x1 minus x2. So v2 x1 minus v1 x2 over x1 minus x2. And now we can substitute in the expression. Our expression, our potential when V is varying along the x alone, our Laplacian equation, solution of our Laplacian equation is here. So when we neglected twice, we got it as this. So we substitute for Vx. So thus the potential Vx will be equal to A. A is V1 minus V2 over x1 minus x2, and then we add, we multiply by x, and then we add on B. B is V2 x1 minus V1 x2, and then this is over x1 minus x2. So this would be our solution of the is there any way we can simplify it further? Those of you who are big mathematicians, can we simplify? Is there any chance that we can make it look even simpler? Everything is on the denominator is the same, so we can add the numerators. Just one of us solve it here, then transfer it there. Assuming that everything is okay, that I didn't mess up anything. So we would have Vx. This would be the same as the V1 x, no subscript, minus V2 x, no subscript, and then everything is over x1 minus, they look the same. So then we would have plus V2 x1, then minus V1 x2. We can make there are things which look alike. So this and this So we have a V1 into x minus x2, and then we add on we add on V2 into x1 minus x. And this is over x1 minus. So therefore, Vx would be equal to, so if we know V1 at the boundary on the other side, and then we know the x, we know the x2, and then we know the V2, we already know the, so we know the x1, the x we have already said this, and then we have the x1 minus x2. This should be able to give us the potential. And we take, this is case 1. This is case 1, only varying in one direction. So assuming we were having on the y and the z, how things would have been. I don't know, is this x minus x1 minus x or x minus x1? X minus x2, that's okay, this and this. Then these two, you have, yeah, it is x1 minus x. I don't know if we did the, this is V2, the minus is on x, and plus is okay, and then the expression I have here, which I see verified, says V2 in x minus x1, and V1 in x minus x2. I don't know how true it is.
That's from the other side.
Where? Which side?
When subtracting the first equation,
I normally say check in the notes and confirm. Check, not in the notes, but check by working through. It's not a big deal. Once you check and go through and get the values of A and B properly, then you should be able to get the right expression. Let's do it too. This one is correct. Only that they put a what? They put a negative here?
Yes.
And then exchange this. Who are those?
I can do it.
Who are those? Yes, it is true. When because I had a pencil which I verified, the negative is put outside, and then it is the other way around. So, any query about this? Because we have done this for Cartesian and chosen just one variation along one coordinate. So if power can't go when I'm teaching. So, has it ever gone?
Yes.
Where?
Once.
Practicals. It went once in practicals for you to go and take lunch. And when you came back, it came back. When you came back immediately, it came back. Any other day, when? I don't remember. Those days I don't remember.
I also don't remember. And there are questions like,
So, power can't go when I'm here. I am a shareholder in Umeme, so if that happened, I'll sack the guy who did it. Good, so we now go to the second do some examples. Start small. After starting small, then we shall be getting. So case 2. Case 2. Suppose V is a function of. Suppose V is a function of the cylindrical, or only the cylindrical, coordinate R. Then, do you remember the Laplacian in cylindrical coordinates? Tell me about it. So Laplacian's equation in cylindrical coordinates is equal to only the other part, the one with the other part. 1 over R. Huh? It is in the nuts. It is in the nuts. We are only going along the R, so we don't need to mention the partial differentiation. Partial differentiation is when you are partially differentiating on one coordinate, partially differentiating on another coordinate, partially differentiating on another coordinate. So since we are only now having variation along one coordinate, we take full blast differential. So this is 1 over R. Yeah? DDR. Inu R. Kali is not there because we are in one coordinate. DVDR. DV. Yeah. And this is equal because this is the grand square. V in cylindrical coordinates, and this would be equal to 0. This is now our Laplacian equation. And for those of you who probably came late or have not bothered to get an idea, the cylindrical coordinates, we have an example of a cylinder here. This banana cables is an example of the cylinder we shall be dealing with, but don't think it is a huge cylinder. So a cable, like a transmission cable, or this one of banana cable, or the antenna for the TV, this is it. So if we have this is the outer cylinder, there is an inside cylinder, in between them, this material you see is what we call the dielectric, is the one which is in the middle. And these banana cables also have their gender. This is female, this is male. And that's how you connect them. That's how they are connected. And if you want to check them out, both of them are there. They are both male and female. So if you want to check them out, check them out. If you want, so if you never saw them. So we in cylindrical coordinates, we have the cylinder, is more now showing the graphics, the GIFs of the sphere bulging, the cylinder plane sweeping as the blue one is getting up, the cylindrical, the Cartesian I didn't bother doing because it is common sense. You did it in O level when you are looking at the box, looking for the plane from this side. And sometimes you see a teacher saying, like, if there is a plane somewhere here, and the damn thing is here, it's just looking in this corner, and we even come with a piece of timber probably and put in, but it says, like, this plane, PQ, the one which, it is very interesting how some people can explain something and it's like as if it is from heaven, when actually it's this iron sheet which you can place in one corner to lie on the wall, this other part. And then if you extend it and slide it, it is the same as drawing the hypotenuse from that corner to here, so that you have the opposite and the adjacent if the angle is there. Then you find using Pythagoras theorem. Pythagoras theorem. Yes, you work. It's my pronunciation, so you got nothing to do about it. When I was in some other place, some lady kept, you know, she thought I was going to be like the pastors who say, when they meet you, when they are sober, they say, God loves you. And then when they are preaching, they say, the mercy of God. So she always wanted to see whether I can say other than water. And she failed. And then one time she confessed and said, I thought you were showing up. You are trying to forge the accent. That's how I talk. So when I'm with normal people, I speak vernacular. Normal. Because when I speak English, I see everyone looking at me as if I'm crazy. And when I speak vernacular, it is okay. Those who were not there, we have this as our Z for a cylinder. This size of the cylinder bulging and becoming small is the R. Sometimes written as S. In the identities in the book I gave you, they are using S. So instead of VR, they will be having VS. If you check out on the identities in the glyphs. And so, then if you draw the coordinates X and Y, and then Z up there, if you were to have this any place here on this as a plane, the one which is it red in the on Mwere? This one which sweeps through, because I didn't come with my cylinder. It sweeps an angle here, which is the azimuth, phi. So now we have these three coordinates, R, then we have Z and phi. Or is the Z the last or phi?
Z last.
Z last. So it is R, phi and Z. So this is the height of the liquid. If we are filling up this cylinder, this is the azimuth, our size of the cylinder, and then the R is how big it can. I think phi would be around the cylinder, and then the R would be how it bulges if you could make it larger. If you were to blow that balloon the telecoms use when they are advertising. When it is deflated, it is small. When you pump pressure, it becomes a huge one. Jerome, what is going on? I've never seen you excited like how you were before I had to call you up. You know I will make you sit in front. And Mary, we are somewhere in front.
There will be signs.
I had never seen Jerome excited this way. At first, I looked there like 3 times and I said, let me first wait. Maybe see whether he's memorizes. But he was. So we move on. We move on and now do the integration. So integrating once gives us what? Integrating. So first of all, before we even integrate, we first multiply by R throughout. So R goes, R0 becomes 0. So then this is differentiating this, so we do integrate. So it's like we do nothing and this is really constant. Yes?
Okay, my question, why is that we separate it, the R and the R?
It is not us. That is Laplace's equation. But that is if you divergence of grad V in cylindrical coordinates, you could probably come up with the expression.
Is it wrong if someone replies
It is what?
Is it wrong if someone replies that did
How? This says that you are differentiate, so you have 1 over r multiplied by the differentiation of this derivative inside. So you can't rush. You first make sure you remove these things here, then remain with this is an instruction. So you can't play around with it. You can't divide by it both sides. Otherwise we would have divided by DDR both sides and we get a 0 here. And then we now remain with this. Then we divide by R both sides, maybe get infinity. And then finally maybe do so. But we do what we play around with the instructions that are there. This is the expression for the power of R. And then on multiplying by R both sides, it goes away. And then on integrating once, you can say integrating for your case, means it's integrating. On integrating once, then we get RDV here equaling to some constant. So constant, some damn constant. It doesn't always be a dumb one. Sometimes it is a nice one. So equals to a constant. Is it raining or what? Let me keep to the script before I get issues. So this is equal to a constant. Or as Fred says, some damn constant. Maria, you see, when I make a joke, I mean that you leave my son alone and you get back to where you were and concentrate. It is not that I was saying that now that the man is excited, you relax. I was being very humble, not to cause problems. At least I was excited to see Jerome excited for the first time during the lecture. Now we are arranging for I'll tell you the puzzle I got when I was still a student. The boys who were looking like, if I use that word you will feel bad. Jerome, don't take it that I'm talking about you. Those who looked like timid are the ones who were being liked by some nice girls, which we didn't understand why. Now, wait. So there was this one boy who used to talk numbers for me. I think he was even praying from some church. I didn't see the woman who caused him problems. But this is a young man who got a first class. This boy was good. He chopped numbers for me. He was one of the first people who did computer science when it was still mathematics, a subject with mathematics. Before the cookies came in, it started as an institute of computer science. Now when we graduated, for us we would be telling him, we went for the Afrostone bash, we danced ourselves here for him, he was always talking about chopping numbers. Now when we graduated, this woman made him to do things that we could not imagine. I hear they would go to supermarket, eat ice cream. He had reached to a time of even borrowing from us. And not paying until when I came. His phone he had even changed. If you get a phone and divert to a number which is not on the network, when they call it, it says this number is not on the network. So we were wondering what is doing. So one time I went to the institute, and what annoyed me was when I asked his friends, they said, they laughed, you know, asking where is Jeremy, for example, and then they laughed. Say, that one, I felt bad because he had helped me so much. I never used to read math. I would read the foundations, read the physics. When it comes to math, I just go, he chops. So it's like he chops me, I just keep breathing in. The thing keeps going in.
I see and remember.
So when, of course, when I would go, I would chop. When I would go, I would also never go. So listen. So one time his dad calls me. When the dad calls me, because I had already gotten that problem, I had already felt bad. You know, if friends are bad, when they find that you are in shit, they laugh at it. They don't even want to talk to you. There are people who don't want to talk to you openly. They don't want to have to be the source of, they don't want, but they know that you are in problem. So when they laughed at his situation, I was touched. So when his dad called me, I didn't, and he was telling me, oh, they are saying Jeremy is at your place. I said, Daddy, because I had never even met his dad, but he had already said I'm daddy of Jeremy. I told him, Daddy, I don't want to mince with words. You need to help your son. The extent he has reached, because he had no experience. He was innocent. And this girl was taking advantage of his innocence. So that's why I'm worried when Maria shifts from here goes there. Then Jeremy becomes very excited. And I know Jeremy's mommy's boy who comes from home comes here. Now he will go home and start scratching himself because he can't miss going back home. So Jeremy, I want you to finish your degree. I don't care about Maria, she knows what she's doing. For you, I want you to finish your what? Your degree. So the dad looked for all the money that they were demanding, from him. Paid the money, got the young man. Now he works in the Ministry of Finance. But we became like non-friends. Because when you are open to people and you open to them, and me, I'm happy because he came to his senses, and he had even won. He was supposed to be going to USA on a scholarship, and he was supposed to be an academic, not in the Ministry of Finance. You would be teaching together here, but that's how he got messed up. But at least I'm happy that eventually he came to his senses. Now he's a man who's, whatever he's doing, I don't care. I'm also doing my stuff. So I know these ladies. We had coursework friends. She comes at your place if she knows that you are through with the coursework. Once the coursework is done, no matter how late it is, she slips off the place quickly. See you tomorrow. So you are asymptotic. It's like you still have the same thought. Tomorrow when you meet in the class, it's like she was never even at your place to pick the assignment. Then when another assignment comes, she's all smiles. Not Susan. I will tell you, let me tell you this final one.
Prophet many.
In our first year, we had one of the innocent looking girls. Then she visited me. And then when I went to buy a soda, when I brought it and I was still looking for the opener, we got like this and from that day I lost interest. That was the first time of visiting me. I went outside and looked for the soda. And then I was still looking on Mikey holders to open the soda. have any, I don't know whether she was being so free with me, but you don't do that in my room. After taking the soda, that was it. I didn't have any. How do you do that? At least if I said it is now okay, you can take, you help me also, fine. But I am still struggling for a name. Rearranging this, and of course putting this, dividing by R both sides. Rearranging the rearranging and integrating again. Rearranging and integrating again, we get that this one will come here, so it will be integrating over 1 bar, and then this will be just integrating the differentiation, which is like we have done nothing. So we get our VR will be the same as the A, then natural log of R, and then we now have another constant, which is B. So for this cylinder here, for the reason why this is uniform, and of course, if you remember when we were drawing the cylinder, we were putting this other part here. We had the inner cylinder, and the inner cylinder here, and our cylinder. And remember, we were putting the grounding here. The grounding is, if you look at this banana cable, this whole thing is metallic. And even these other ones which are male, these other pointed ones which touch the other, whatever, they are also open. So that is the grounding. No bother. Even if you touched, you are not going to distort the signal. And that's why we were trying to draw, and this grounding we were putting on this other one, and then V nut here is because of this kind of construction, or the way they are manufactured. And we shall know why they are just a small bit here, is when you now have to curl the E and B in order now to push them into this wire and then transfer them to the TV, or to the whichever way you are coming from, whether you are from the decoder to the TV or deck to the TV. And that will be the mixer, as DJ says. So if we do this, then now the task we have is to get the constants A and B, and we do that using the boundary conditions. So, but then on this other side here, on the surface here, at a given radius R, then we have the potential being the same. For example, for these banana cables, the potential is the same along this. It is zero. It is grounded along this one. So the equipotential surfaces are given by the equipotential surfaces are given by R equal to constant. At some constant radius R, you have the surface, all those surfaces will be having the same potential, hence equipotential surface. So related to this kind of first scenario we are taking is a problem of related to, I just want to make sure that I will be able to, I was supposed to finish. So related to this, to the problem of coaxial, transmission line. Transmission line. And that of the coaxial capacitor. And that of the coaxial capacitor. So the coaxial capacitor, this example, for example, this banana cable. I don't know why they call them banana cable. They don't have anything to do with banana. I can rename what? Ben cable? But I have to get the explanation of why I am changing the name. So we got the our banana cable. Okay, our capacitor, but the example we have is the banana cable. So if we have this inside the cylinder, and then we have this outside cylinder here, grounded. I've showed you how it is, the grounding is like. So we have this one grounded. It's open. It is even all these oscilloscopes. The probes were having this issue. So if this one is of radius B, the outer one, this one is of radius A, the inner one, and then the potential on this grounded one is equal to 0. This is VD equal to 0. And so I don't want to rush there. And this is V naught, the one which is on the inside. We choose. Why go on now? I leave it to so that because time is not our best talent, and I'm not good at rushing. But let me finish this part, then you can do the capacitance, where you get the potential and the charge, and then you get the capacitance in your free time. So choose the potential for this inside cylinder to equal to V naught, and the one on the outside on V grounded, which is equal to 0. So if we choose so, this means that if we put in the expression for VR equaling to A in R plus B, so when we have V equal to V naught, this V naught, it is V naught when the radius is equal to A. So that means that V naught is equal to A in A plus B. And this would imply that 0 equals A in B plus B. The rest is algebraic gymnastics. So then we have that V naught is equal to, I've already put that, and I don't want to repeat this. So this would imply that the V naught is equal to A inum. I'm jumping this step since I have put them here. So this would imply that V naught is equal to A inum in A minus in B. And this would imply that the constant A is equal to V naught over ln A minus ln B, using the rules of logarithms. The difference in logarithms becomes the logarithm to the same base of the which one do they use when you find them? Thus, 0 would be equal to minus V naught over natural log of B over A. This is B over A. Okay, it is A over B, but you can say minus B over for selfish reasons. So this would be equal to minus natural log of B over A. And then this would be natural log of B plus the constant B. And we can make the constant B the subject and get B naught over natural log of B over A. And then natural log of B. So substituting in our expression for the potential here, then we come up with the VR is equal to minus B naught in R over natural log B over A, then plus V naught natural log of B over natural log of B over A. Please do this on your own so that you are able to get it in an easy way. This will be V now over natural log B over A, and then natural log of B over R. And this would be the potential if we only consider the variation of the potential along only one coordinate. So as an exercise, show that show that the capacitance C is equal to 2 pi epsilon N over natural log of B over A. But if it is a transmission line, you can express it in capacitance per unit length. And of course this L will come here to C over L being equal to that. And I was trying to rush like this and finish this part since we have a long time to meet again on Monday.